Hello everyone, this is Emil Naruto. Welcome to my channel. So, 1 minute. Mm, okay, it's not working. Okay. Okay. So today in this video, I'll be discussing about the asymptotic asymptotic notation. This is all a part of designing an effective algorithm, right? So this is the part of analyzing an algorithms, right? We have algorithm 1, we have algorithm 2, and so on. Out of all these algorithms, if I want to solve any particular problem, so I need to analyze all these algorithms and I need to pick that particular algorithm which is the best for me to solve this particular problem, right? So while analyzing a problem, we have already seen what is meant by time complexity and what is a space complexity. We have already discussed, right? So now these asymptotic notations are very much important when we consider this particular time complexity scenario. So now, for example, let's imagine this is my algorithm. Okay, this is my algorithm. And now this is my input data. So if you pass some kind of input and in return you will get some kind of output. This output will be processed by our algorithm, right? So here our input, for example, if just imagine if I say a is equal to 10, so this input is a very is a very minimal in his in its quantity, right? So what if I say, what if I add 1 0 here? Of course it's somewhat greater than the previous input, right? So 100 is much greater than the previous input, that is 10. And what if I add another 0, that is the 1000 here? So obviously it will be much more greater than the earlier two previous outputs, right? So here, so here, while analyzing an algorithm, right? While analyzing an efficiency of an algorithm, the input size, that is the n here. So the input size, that is n, is very much important. It plays a very crucial role while analyzing any algorithm. So what if our input size is large? What if our input size becomes large? Then the order of growth is very much important. Order of growth in the sense here, order of growth. Order of growth in the sense it's an approximate time. It is the approximate time that is required to run a program, right? For example, if I have a is equal to uh, a is equal to, I'm asking my user to enter some kind of input, right? So I'm asking my user to enter some kind of input. So uh, and then I'm saying if my a is greater than 10, print something like print I. Okay, and else I'm saying, sorry, elif I'm saying elif a is less than 2, print by. I'm also saying else print get lost. Okay, so these are all the uh, statements I have already passed in my programming, in my program, right? So here, just imagine here, what will be the input here? I'm asking my user to enter some kind of input here. So if he enters, example, if he enters, let's imagine 5. So A will be the 5, right? So 5, is it greater than 10 or is it less than 10? Obviously 5 will be less than 10, right? So it will be, it will goes into the category here, that is the else. Why? Because this statement is wrong. Why? Because A will never be greater than 10. Why? Because our A value is 5. So this statement is wrong. So it enters into the elif block of code. So here 5 is less than or 2, or if it is greater than 2. Obviously 5 is greater than 2, right? So this statement will also be wrong. So obviously it enters into the next block of code, that is else block. So it will prints out get lost, right? So this will be the program, basic program. So order of growth would be that particular time, approximate time to run a particular program. So that would be our order of growth, right? Now, what happens is if our input size is increasing, like at first the user has entered some 5, a equal to 5, and then the user has entered some 50 and then 500 and so on. If the input size is increasing, then this particular approximate time, that is the order of growth, will play a crucial role while analyzing an algorithm, right? So this particular order of growth ignores the constant factor needed for the fixed operations, right? And focuses only on the operations that are proportional to the input size. I'll explain you what does this particular statement mean. Okay. So before that, I need to show you one thing. See here, just observe this. See, so we have certain kind of terms, that is, this is the constant time, and these are all nothing but the these are all nothing but the orders. I have already explained you order of growth, right? So this would be the constant order of growth, and this would be the logarithmic order of growth. This would be the linear time order of growth. This would be the quadratic order of growth. This is the exponential order of growth, right? So I'll explain each one of those. Just have a look at. So this constant order of growth is actually saying when an algorithm has a constant order of growth, okay, it means that it always takes a fixed number of steps, no matter how large the input is. So what does that mean here? So it means, for example, our input size is maybe 5 or 50 or 5 lakh or whatever it may be. Whatever may be the size of the input is, but still our algorithm, uh, if it is having a constant order of growth, then it will usually considers a constant line, right? It will usually prefers a constant order of growth. That means no matter whatever may be the size of input, it will still be in a position of constant over the entire input size, right? So if it is 5 also, if I mark this 5 as my input, then also it will be in the same constant position, that is this constant uh, horizontal straight line. And if I mark my input size as 10, then also it will be in the same constant position. If I mark my input size as 15, then also it will be in the same constant horizontal line position, right? So this would be the scenario of constant order of growth. Now this is my logarithmic time, logarithmic order of growth. So what does this mean? When an algorithm has a logarithmic order of growth, it increases proportionally to the logarithm of the input size, right? So it will usually increases proportionally, and then it maintains some kind of constant gesture here, right? So this would be my On the y-axis, if it is my input size, and on the x-axis, this would be my logarithmic order of growth. See here, this would be my input size. If it is 5, or if it is 10, or if it is 15, it will proportionally increase. Why? Because this is an logarithmic order of growth. On the y-axis, you will be having the input size. You just don't need to bother about all the uh, uh, functionalities behind this. Okay, you just need to remember this kind of concept. What do you mean by the constant of order of growth? What do you mean by this logarithmic order of growth? You just need to remember, and I'll explain all these concepts in greater detail in the further videos, right? So this would be your input size, and this would be my logarithmic order of growth. Order of growth, right? So this is indicating when our algorithm has a logarithmic order of growth, it increases proportionally to the logarithmic of the input size. Depending upon this particular logarithmic of the input size, it will usually tries to increase proportionally. So that's what it is explaining. Okay. And now when you look at the next slide, it would be the linear order of growth. What does this mean? Linear, the name itself is actually explaining that the order of growth would be in a straight line, right? So what does that mean? So for example, for 0, it will increase 0, right? For a one particular point, it will increases to one particular point like this. And for 200, it will increase like 200 like this. Okay. So it's not, the diagram I'm drawing is not accurate. See, I'll explain. See, for 150, let's imagine this is 100. Okay. Let's imagine this is 100. So for the 100 input size, my my algorithm will usually has a linear order of growth of 100, right? For 200, just imagine, for 200 input size, my linear order of growth would be having 200, right? So likewise, it will usually directly proportional to the input size, my linear order of growth. On the x-axis, it will have linear order of growth. On the y-axis, it usually have input size n. So this is directly proportional to the input size. Whatever may be the input size is, it will usually increase in a directly proportional way. For the input size 500, will usually increase 500 times of my linear order of growth. So this would be the scenario. Now, when you look at here, this would be my quadratic time. When an algorithm has a quadratic order of growth, its steps increase in proportion to the input size squared, right? So it will usually squares up and gets increased. That's the quadratic time here. Just remember this particular shape of the graph, right? This is the exponential. It will instantly increases. Why? Because it's the exponential, right? That is the super polynomial order of growth. What do you mean by this super polynomial order of growth? For example, if I have few letters like maybe a and 2 and hash symbol and at the rate and dollar symbol and 6 b d 9 k. So I want to make use of all the characters listed in this particular box, and I want to make a strong password. So how to do that? So one possible way could be maybe capital A at the rate 6B 9D 2 hash K. So this would be one possible way. So likewise, how many possible ways are there to create such strong password using all these characters listed in the box? So for that, we need to pass through all these elements listed in the box. So I need to touch this element, this, and I also need to form some all the possible permutations and combinations of all the characters listed in the box. So for that, I need to pass like I need to match A with the 6, A with the B, A with the 2, A with the hash, A with the at the rate, A with the dollar, A with the D. So likewise, I need to form multiple permutations and combinations. So for that, I need to touch up all the things listed in the box here. So we call that as a super polynomial, right? So when we find any super polynomial in our algorithm, we usually then our algorithm usually has a exponential kind of order of growth. That means it will usually increase exponentially high for our input size. On the x-axis, it will have the input size, and on the y-axis, it will have exponential order of growth, right? Okay. So when you observe all these things holistically uh, on the same graph, it would be very much meaningful to you. See here, see here. So this would be my constant here. This would be my logarithmic. This is my exponential, and this would be my linear. This would be my quadratic order of growths, right? So these are all the order of growths respectively. So this is the constant, logarithmic, and this is the linear. Why? Because it's in the straight line manner, and it's the quadratic, and it's the exponential. So these are the kinds of order of growth we have. And when I say order of growth, we need to analyze the algorithms depending upon these order of growths, and we need to pick that particular best algorithm which satisfies this asymptotic kind of analysis, right? So we pick that particular algorithm which uh, which has got proven in this asymptotic analysis. So in this asymptotic analysis, we have famous three notations, right? So following asymptotic notations are commonly used to calculate the running time complexity. That means, see, we have few notations. See, we have few notations. Most famous notations. The first one is the theta notation, and the second one is the big O, big O notation. The third one is omega notation, right? So in this video, I'll be explaining this theta notation, right? So, but in briefly, I'll explain each of these, but in greater detail, I'll only explain this theta notation in this particular video, and in the later videos, I'll explain the remaining two notations, that is big O and the omega, right? So, what do you mean by this theta notation here? Theta notation means it denotes the worst case. It usually represents the worst case running time of an algorithm. Usually represents the worst case running time complexity with a tighter bound. So you need to remember this particular word, that is the tighter bound here. So what do you mean by this, the word that is the tighter bound here? For example, uh, let's imagine this is my running time. Okay, this is my runtime complexity. Okay, of an algorithm. So for our algorithm, we have the best case scenario and the worst case scenario and the average case scenario, right? So best case scenario would be that where our runtime would be very minimal, right? For example, uh, I can say that my worst case running time would be uh, up to this, let's imagine up to maybe 50 seconds. This would be my worst case scenario for my algorithm. That means my algorithm can maximum, my algorithm can take up to 50 seconds maximum. So this would be the maximum amount of time that is taken by my algorithm. Beyond that, there is no scope of, uh, there is no scope of any taking much more time. Okay. Beyond this, my algorithm won't take any uh, time. So this 50 seconds would be my upper limit, right? So this 50 seconds would be my upper limit. And here, what is the best case scenario for my algorithm? So in the least, in the least amount of time my algorithm usually takes is, let's imagine 10 seconds. So my algorithm will usually takes 10 seconds in the best possible scenario. So this would be my lower limit, right? So if I define lower limit and the upper limit, so this would be my notation here. For example, just imagine if I say big O, that means it is the worst case running time complexity with an upper bound. Okay, see here, I'll explain each of this. Don't worry. So here I'm keeping the heading theta. This is the theta notation, and this is the big O notation, and here this is my omega notation, right? So I'll make a distinctive note. So first of all, what do you mean by the theta? Theta means it is the worst case running time complexity. Worst case running time complexity with a tighter bound. You need to understand this tighter bound. Tighter bound in the sense, if this is my running time complexity, I only have same upper bound and the lower bound. For example, this bar would act as my upper limit or upper bound. Okay, and this bar itself will also act as the lower bound or the lower limit. Okay, so my upper bound and the lower boundary will also be the same. If I consider this theta notation, my upper limit and lower limit will also be the same one, right? So I'm saying exactly my algorithm will usually require some certain amount of time. Maybe let's imagine maybe 35 seconds. Okay, I'm saying in the worst case time complexity scenario, my algorithm will usually takes 35 seconds of time. Beyond this, it won't take such amount of time, right? I'm saying this exactly. So theta notation would be defining the worst case time complexity exactly. Why? Because I'm already defining upper limit and the lower limit for my algorithm. And this is the big O. So what do you mean by this big O? This also denotes worst case running time, right? With an upper bound. This ensures the function never goes wrong beyond that upper bound. That means this is my runtime complexity. Okay, so it will usually define some kind of upper bound. So it will usually defines this is my upper bound. So this is my upper limit. Let's imagine this would be my 75 seconds. Okay, so this is usually saying that my algorithm won't go beyond this 75 seconds of runtime complexity. Okay, my algorithm won't take greater than the 75 seconds of time to run particular program. So this would be my big O. Why? Because here I'm defining my upper limit or upper boundary. Okay, so beyond this there won't be no time taken by my algorithm. And when I want to talk about this omega, so this denotes the lower boundary of an algorithm. That means this would be my best case runtime complexity. So this would be my best case runtime complexity So it measures the best amount of time to execute the algorithm. That means this, let's imagine this is my runtime complexity, right? So my algorithm will say like beyond this, I won't take much time, right? So this would be the least possible amount of time taken by my algorithm to run a specific program. So this would be my lower bound or the lower limit here, right? So this would be the lower limit. For example, I have certain kind of lines. So maybe a equal to 20 and if condition and then the elif and then the elif and so on, so many conditions. And then finally we have the else condition. So this is my program, right? So if I want to run this program, it will usually take some kind of time. So here in this particular omega notation, here it's saying it is actually explaining that my algorithm will usually take the least possible time. That is, let's imagine this is of 10 seconds, right? So my algorithm will usually takes 10 seconds in its best possible way. That means this would be the least amount of time. So omega notation is actually explaining this is the best case runtime complexity to run a specific program, right? So by this, I have already explained briefly about what is theta notation, what is big O notation, what is this omega notation, right? So now I'll be explaining what is mean by theta notation in greater detail. So theta notation. So those who haven't watched the previous videos, that is about time complexity and the space complexity, I'll keeping those links of videos in my description. Just go and watch it. Why? Because without watching those videos, you won't be understanding this particular video, right? So earlier I have already explained about time complexity. So from that video, from that program, I mean from that piece of code, I'm considering some kind of equation like t of n is equal to c1 plus c3 into n plus c5 into n. If you don't, I mean, if you didn't understand what is this equation mean by, just go there and watch that time complexity video first. You will definitely get understand. So what I'm talking about, right? So then come back here. Okay. So this particular function, you can call this t of n as a function. This function usually describes the worst case. Usually describes the worst case runtime. For my first example, which I have already explained in the time complexity video, right? So just go there and watch that video. So for large input size, for example, if my input size that is n, this is my input size. If my input size is actually increasing, that is, if my input size is very large, then the worst case scenario time would be, then the worst case runtime would be theta of n, right? So this would be my worst case runtime. For example, if I want to explain, then let's imagine I have an algorithm 1, okay, and I also have an algorithm 2. If the worst case runtime has a lower order of growth for any algorithm, that's the efficient of two algorithms, right? For example, this has some kind of order of growth and this has some kind of order of growth. But out of these two order of growths, I will prefer that particular order of growth which is of lower. That means I will only choose lower order. I will only choose lower order of growth. Okay. So I will only choose lower order of growth for any algorithm. So that the algorithm which is having that lower order of growth would be picked up as the best efficient algorithm, right? So I need to look for that particular algorithm which is having lower order of growth. And that algorithm will usually be picked up as best efficient algorithm out of all the two algorithms. So, but here, due to some constant factors and lower order terms, an algorithm's runtime has a higher order of growth, right? I'll explain this with the help of an example. For example, I'm writing some kind of equation here, maybe t of n is equal to theta of f of n. So if this is the function here, so if this is equation, so how do you, uh, what does this equation is usually explaining? So what is meant by the theta here? Theta is nothing but the worst case runtime is nothing but the theta. And what is this f of n here? So this f of n would be my function, right? So just assume, just imagine, if I have the constants that is c1, c2, and n suffix 0 exists. Okay, if I have these constants in my equation, okay, then how do I form some kind of relationship? I usually say 0 less than or equal to c1, that is my first term, right, of my function. I need to represent my function here, that is f of n, this function, right? And then it would be less than or equal to t of n, that is this particular thing, t of n, and this would be less than or equal to c2, that is my second constant term, c2 of f of n. This is my function again, this function, right? And I will say for all n is greater than or equal to and 0, right? So this would be my equation. See, just imagine, this would be my first constant term, this would be my second constant term, and this would be my third constant term, right? So these are all the constants. You just imagine these constants have been existed in my equation, then I would form some kind of relation, that is 0 would be less than or equal to c1 of my function, and less than or equal to t of n would be less than or equal to c2, that is the second constant of my function f of n. So this would be my function. So in general, in practically, so it is saying that maybe, so it's actually saying for the function t of n belongs to, that is this particular t of n is actually belongs to set of functions, that is theta of f of n, and if, so this equation is actually explaining about this thing, right? So here t of n, that is this t of n is actually belongs to set of functions. Set of functions means this theta of f of n, right? And we are actually saying if constants c1, c2 exists, c1, c2 exist, then what happens? Then t of n lies. So we are actually talking about this particular equation. We are saying if constant c1 and c2 exist, then t of n lies in between c1 of f of n and c2 of f of n for all the values of n, right? So if this condition is true, then we can say f of n, that is the f of n, This is our function, right? So this function is asymptotically tight bound for P of n. So this would be our condition here. See here, this particular box, this box is our condition here. If this condition is true, then we can definitely say that f of f of n, that is our function, is asymptotically a tight bound for T of n. Why? Because it is lying in between the C1 of f of n and C2 of f of n. So we can usually say f of n is asymptotically tighter bond. See, this is my, so it is acting. See here, C1 of f of n and C2 of f of n is actually acting as a tighter bond. If this is my runtime complexity, here this would be my lower and this would be my upper. Both are the same itself. Both are the same limit. So hence it is asymptotically a tighter bond for the T of n, right? So this would be the example. So diagrammatically, how do you represent this kind of a condition here? See, I'll draw some diagram. See, for example, uh, okay, so this would be my first constant, that is C1 of f of n, right? And this would be my second constant, that is C2 of f of n. And there lies the my function, that is the T of n. This would be my T of n. So here, by having a look at this graph, you can easily say that my T of n is actually lying in between the two constants, that is C1 and C2. So hence we can definitely say that uh, f of n is asymptotically a tighter bond for my T of n, right? So this would be the junction where all the terms are actually lying here. Both the three graphs are actually in contact here. That is my n0, and this would be my n here. So hence we can conclude that T of n is equal to theta of f of n. What does that mean? That means f of n is asymptotically a tighter bond for my T of n, right? So this is an example. Uh, So, and let's have a look at another way of explaining the things. So let's imagine I have f of n is equal to my f of n has an equation that is n square plus n. Okay, so we have f of n is equal to n square plus 1, and this entire equation is considered as theta into n2. Okay, just imagine like this. And we need to identify the constants. What are my constants here? C1, C2, and 0. We need to identify these constants in our equation. So by that, after identifying all these constants, we can definitely form some kind of relation. That is my condition. What is my condition here? 0 will be less than or equal to C1 into C1 into n square less than or equal to n square plus n less than or equal to c2 into n square, right? So this equation is very much similar to the previous one, and here what is the difference here? Difference is in between, difference lies in between the terms here. There we have used a t of n in place of this. There we have used a t of n, right? Earlier we have used t of n, but now here the term is n square plus n. So c1 and c2 are the earlier constants. So that's the thing. And hmm, okay, now what I'm doing is I'll try to divide this. I'm dividing this by n square. I'm dividing the entire equation by n square. So what happens? Just have a look. 0 by anything is obviously 0, less than or equal to c1 of n square by n square. What happens if I divide c1 of n square by n square? Obviously both will get cancelled, and less than or equal to, if I divide this entire thing by n square, what happens? N square by n square is nothing but 1, n by n square is nothing but 1 by n, and less than or equal to, if I divide this entire thing by n square, what happens? I'll get c2, right? So my final condition would be 0 less than or equal to c1 less than or equal to 1 plus 1 by n less than or equal to c2. This would be my equation. Here lies some condition for all n is greater than or equal to n0. Okay, so this would be the equation. And now what if what if I assume some kind of values for my constants, like we have c1, c2, and we have uh, n0, right? What if I take some values? What if I imagine some values? Let's imagine, uh, I'm just taking this as an example. Okay, c1 is equal to 1, c2 is equal to 2, n0 is equal to 1. And if I substitute all these values in my equation, then what happens? Okay, if I substitute all these values, then what I'll be getting is, just substitute c1 in the place of c1 here, just keep 1 here. Then what happens? 0 less than or equal to uh, n square less than or equal to n square plus n less than or equal to 2n square. Okay, so this would be the for all n greater than or equal to 1. So what is this equation actually? So this equation is nothing but, if we substitute, I mean, if we assume c1 equal to 1, c2 equal to 2, and not n0 is equal to 1, then what happens is these conditions satisfy the definition of the notation, right? This condition satisfies the definition of the theta notation. So if I apply, then what happens? Ultimately, f of n is equal to theta of g of n. That means you can say that f of n is equal to theta of n square. So in the place of n square, we can also write g of n. So this is an example. Now let's have a look at another example. This is the final example. Okay. So let's imagine we have a equation f of n is equal to n square by 2 plus n by 2. Okay, and just identify our constants, that is c1, c2, and n0. Just find these things and form some condition here. So 0 will be less than or equal to c1 into n square by 2. C1 is the first constant term here, less than or equal to n square by 2 less than or equal to C2 into n square. Here also, for all n is greater than or equal to n0, this would be the condition. If I choose C1 is equal to 1 by 5 and C2 is equal to 1 and not is equal to 1, then what happens? My equation would become 0 less than or equal to n square by 5 less than or equal to n square by 2 plus n by 2. Sorry, I have missed something, like n by 2. N by 2 less than or equal to n square. So this would be my equation. And here also we need to mention that for all n is greater than or equal to n naught, means how much? N naught is equal to 1, right? So I need to mention n is greater than or equal to 1. Okay. Mm. So this equation ultimately becomes n square by 2 plus n by 2 is equal to theta of n square, right? So why? Because n square by 2 plus n by 2, uh, I mean, see here, this n square by 5 would be asymptotically will become the tighter bound for this n square by 2 plus n plus 2. So theta of n square. See here, we just need to pick this notation n square. We will forget about the constant terms, that is 5 and here 1. Okay, we'll forget about that. We ignore that. So this is possible with the constant terms of values c1 equal to 1 by 5, c2 equal to 1, and not is equal to 1. So therefore, finally, what we can say is f of n is equal to n square by 2 plus n by 2 is equal to theta of n square. It shows that given function has the complexity of theta of n square, right? As per our theta notation definition. So theta notation provides a tighter bound for the time complexity of an algorithm. Okay. So yeah, that's all for this. I'll see you in the next video. Bye bye. Take care.